Hello everyone. So in this video I'll be explaining the demo of my project which I did for Intel InnovateFPGA contest for 2021 to 2022. In this project I implemented accelerator for orthogonal recurrent neural networks on the fabric of DE10-Nano, and the accelerator was a quantized accelerator which was written in Intel HLS. So the board has already the Linux running on it, and all of the commands and the instructions are also provided in the GitHub repository. So first of all, let's first SSH into the board by also forwarding this port 9090, which is the port for Jupyter. So we will use the Jupyter notebook to see the demo. So in this directory I already have cloned the repository ORNN Nano, and let's go inside it and go to the host. So here I have the main branch, which gives you the demo for the image recognition. And let's just launch the Jupyter by going into sudo mode. Let's launch Jupyter, and we can just copy paste the link which is given by Jupyter to the browser. So let's copy this thing. So the board is actually connected via LAN cable to my MacBook, and it has forwarded the Jupyter port. So here you can see the IPython notebook for the DE10-Nano demo, ORNN demo. So let's open the Jupyter notebook, and first the command make install, what it will do, it will just upload the RBF file onto the programmable logic block of the FPGA, and after that we will do some necessary imports, and let's load the dataset. We can see the shape of the dataset is correct, and let's define a function for quantizing the inputs and packing it to 64 bits. And we will define here some register addresses which are already given by the Intel HLS compiler in this ACCL top csr.h file. We will next define some IO input-output buffers to hold the input and output of the accelerator, and then we will instantiate the driver which will be coming from device driver, and this device driver and the CMA buffer, they are defined in PySci file, and it is actually Python. It has all of the Python host code and drivers to control and communicate the accelerator. Let's just instantiate the driver, and we will see some test image of an MNIST dataset, which you can see it's also MNIST images. Oh, okay, I need to load the dataset here, MNIST, and then we can see the image here. You can see, and let's quantize the image. We will use the given quantize function to quantize and pack the image. So after quantization to 4 bits, it doesn't look much of a difference, it doesn't make much difference. And let's pass the accelerator the buffer address, and let's start the accelerator and wait till it gives the prediction, and it's done. And let's visualize the results. So here the input was 7 and the prediction was also 7, and it was given by the accelerator, because here you read the array B of the CMA buffer which was connected to the accelerator output. So here you can see you connect output buffer register as array B. So array B will have the output written on this, which you will apply argmax to get the maximum index. Similarly, you can run the inference on the whole dataset by running this cell, which will take a little bit of time because it's the sequential processing in ORNN. But after running the inference for 10,000 images, I get 90% accuracy, and the average frames per second were around 1454 frames. And then finally, you can unload the RBF file and unload the accelerator. Similar demo can be also observed by using the notebook for the audio MNIST branch, which is also given. You can check the notebook in the repository. I will not show the demo of that because it's going to be similar, but instead what I would like to show is the accelerator definition on the top. So this top.cpp file under HLS has the top definition of the accelerator. So here I define some internal streams and input output streams, you can see, and the input buffer is coming from Avalon memory master interface, similarly the output buffer as well, but they both have Avalon register argument as well to give the address of the buffer, and the data will be fetched from memory mapped interface. Similarly, the sequence length of the input will also be coming from this register argument interface. And then the first function is actually reading the data from the DDR memory of ARM processor and putting it into the stream. And then you adjust the stream width according to the PE and SIMDs, which defines the accelerator. So here you can see the definition of orthogonal recurrent neural network layer written in HLS. It can work with different input dimension, recurrent dimension, number of classes. You can control the input and recurrent SIMDs for input parallelization, and you can similarly use PEs for output parallelization. This is all templatized function. You can scale it up, scale it down, and it has some arguments for input type and recurrent type, which is essentially the bit width and the type of input and recurrent connections. And at the end it will give you the outputs in the stream, and then you will use the stream, which is column stream, output stream, and you will write the stream data back to DDR. So now from first you read the input from DDR, put it to the stream, and then you write the output from the stream to DDR again. And if I would like to show you the definition of ORNN layer, you can just open the ORNN.h. Similarly, here in the for loop, you can see the linear layer for the input gate, and then this linear buffer is for the recurrent connection, recurrent gate. And then you apply mod relu function for the activation function. What it does, it first add these both streams, which is input and recurrent, and then apply the nonlinearity on top of it. And the output of this goes to the output gate, which just converts the output to the number of classes, map it to the number of classes. And then you can adjust the stream width again to cater for the 64-bit bus alignment on the Avalon interface, and the PE and SIMDs here, because as you change PEs and you scale up, you need to have the stream converter which converts the respective PEs and map them to the 64-bit interface. So similarly, you can check the definition of linear layer. This is all templatized functions which works with different dimension, different input bit width, different SIMDs and PEs. You can define input output parallelism, and you can check the repository for your learning, and you can explore the code here, which is all templatized. So thanks for watching, and I think this is it for the demo, and bye bye.